seminar. So Anthony is a third-year PhD student under my supervision in Toulouse at IRAP. So he's working on the seismology of subgiants and interested in the structure of convective cores and the extension of convective cores. He's planning to defend his PhD in December this year. He has one paper published in Astronomy and Astrophysics. He will mention it today, and he's currently working on two more papers. Yeah, he will be looking for postdocs for after the end of his PhD in December. So Anthony, I will let you present your work.
Okay, so I start to share my slides. Okay. Is it working? Yeah,
Yes,
okay.
very well.
So thank you, Sebastian, for that introduction. So yes, so my work is dedicated to how we can probe the core overshooting using subgiant asteroseismology. And therefore, during this talk, I will first introduce briefly the convective cores as well as the seismic modeling of subgiants. After, I will talk about a work that has been published in Astronomy and Astrophysics two months ago, and that is dedicated to the modeling of a subgiant observed by Kepler in order to retrieve constraints on its former Mainsequent core extension. After, I will talk about a work in progress, something that is slightly different as it's not directly related to the seismic modeling of subgiants, but rather that investigates the impact that can have both the central mixing and the nuclear reaction networks on the size of the convective core. And after, I will conclude. Okay, so we found convective cores in stars that are more massive than 1.2 solar mass, so the blue region, that Kippenan diagram on that figure 1. And classically, the limit of those convective cores is defined by what we call the Schwarzschild criterion, which tells us that the region of the star is convective if the radiative gradients is bigger than the adiabatic gradients. However, we know that different physical processes can extend this core beyond that classical limit. Those processes, they can be the overshooting or penetrative convection, where blob of fluids will overshoot beyond that classical limit because of their inertia, but also other processes can happen, such as rotational mixing or semi-convection. And today, those processes, and even more the way they interact one with each other, is poorly theoretically described. And therefore, overshooting, which englobes all those phenomena as one, is modeled in stellar evolution code in simple ways. Today, there is what we call the step overshooting, which is a crude extension of the convective core over a distance DOV that is parameterized by a parameter alpha OV that is highlighted in red here. But we can also implement what we call a diffusive overshooting, where the region just above the convective core will be mixed following a diffusive coefficient DOV. And we can see that this coefficient as well is parameterized by a free parameter FOV. So those two parameters in both cases have a strong impact on stellar evolution as well on the age estimation of the star. I illustrate this in the figure 2, where I plotted evolutionary tracks of the very same model, stopped at the same age, but with different size of a convective core, with different value of alpha overshoots. And we can see that if we don't include overshoot, at 4.5 gigayears, the star will already be in the subgiant phase. But if we include overshoot with alpha OV equals 0.2, it will still be in the main sequence. So we need observational constraints to put constraints on those three parameters. So there are different methods for that. The historical one, if I can say, it's the study of observational HR diagrams of open clusters. On figure 3, we can see the HR diagram of the Pleiad cluster, as well as isochrones that are plotted either with or without overshoots. Also, in the last decade, especially Claret and Torres focused on the study of binary stars, and thanks to their strong evolutionary constraints, they obtained a constraint on the FOV parameter. We can see this on the figure 4, where we can see that there's a trend of increasing FOV with the mass before reaching a plateau for masses that are superior to 2 solar mass. And of course, if I talk today, it's because asteroseismology can, of course, help us to probe and to constrain this alpha V parameter. So for that, we can study solar-like oscillators, which exhibit P modes during the main sequence. On figure 5, I show as an example results that have been found by Sabatier a few years ago. Here as well, we can see an increasing trend of the alpha V parameter with the mass. And also for more massive stars, which exhibit G modes during the main sequence, we can study them. And actually, the G modes are very convenient, if I can say, because they probe directly the border of the convective core, and therefore allow to retrieve some constraints. For example, the study allow to favor diffusive overshooting over step overshooting. However, as I said, as Sebastien said during the introduction, and as you saw in the title of that presentation, my work directly study the main sequence who have a convective core, but rather do an autopsy of those stars by studying the subgiant that they became. So here I represent a scheme of a typical structure of a subgiant. So there's no convective core in the subgiants. They are an inert helium core that is the remnant of the former convective core. Above that core, there's a hydrogen burning shell, and we believe that both those structures are quite sensitive to the former main sequence structure. And also, fortunately, if I can say, we find in those stars a convective envelope which will excite modes in the star, and therefore subgiants are solar-like oscillators. So to understand the seismology of those post-main sequence stars, let's go a little bit before the end of the main sequence, and I will say things that I'm pretty sure you are all familiar with, but I will talk about the seismology of main sequence solar-like oscillators. So such oscillators during the main sequence exhibit high frequency pressure modes that because they reach the surface and therefore as visible, as we can see on the propagation diagram. However, the low frequency gravity modes are trapped within the stars, they don't reach the surface and are therefore not visible. Because of that, we obtain this kind of phase diagram that is not observation, but a model, but typical of this kind of oscillators. And we can see that both the radial frequency in blue and the dipolar frequency in red are stacked up in that phase diagram in ridges, which is typical of pure pressure modes. However, after the terminal age main sequence, after the end of the main sequence, so the radius of the star will increase, which will lead to a decrease of the main density and therefore to a decrease of the frequencies of the pressure modes. And contrary, because of the Marrow effect, the central density, the core will contract, which will increase the central density and eventually increase the frequencies of the gravity modes. So that at some point, the G modes and the P modes will be of the same order, which will lead to a coupling between the G and the P cavity, which will eventually lead to the apparition of mixed modes in the observed spectrum. So here as well in figure 9, it's a Hessian diagram that comes from a model of a subgiant stars. We can see that the radial modes in blue are stacked up vertically, closely as what we saw with main sequence stars. However, for dipolar modes, it's totally different. The dipolar ridge have some kind of weird pattern, and especially we can notice that two modes that are circled in red went far from the dipolar ridge. Those modes are called G-dominated modes because most of the energy is actually in the G cavity. So those mixed modes are interesting thanks to the dual pressure gravity natures. So like pressure modes, they reach the surface and therefore are visible. And like gravity modes, they probe the very central structure of the star and are sensitive to the evolution of the star. So they are kind of the best of both worlds. And thanks to that, we observed an increasing interest in the literature toward the seismic modeling of subgiants, especially thanks to that high sensitivity to the evolution. They allow to retrieve precise parameters, which can be quite interesting. For example, if you want to constrain a planetary system. For example, here as an example, I took a Hessian diagram from Huber et al. 2019. That is a subgiant observed by TESS, and that is a host of a planetary system. But another point of view is that high sensitivity to the structure can also allow us to investigate the stellar physics. So we can investigate rotation, as for example, Sebastien did last year, and also the internal structure of the subgiant. So what we can wonder is, what can we probe thanks to that mixed mode? What can we, what information on the structure we can get? So to understand that, I'm representing here a typical propagation diagram from a subgiant, and we can see the P cavity in orange that is defined by the lamp frequency, and the G cavity in blue that is defined by the Brunnweiss-Sala frequency. Especially here, I draw your attention on the red term on that Brunnweiss-Sala frequency that is called nabla mu, and that is the composition gradient that is plotted in red on that propagation diagram. And especially we can see that nabla mu is directly related to the structural features of the hydrogen burning shell, and therefore is of prime interest for us. So the frequency of mixed modes depend on two things mainly. So the first is the frequency of the associated G mode. So we know, thanks to the asymptotic theory, that the frequencies of the G modes are related to the integral of the Brunnweiss-Sala in their cavity. And therefore, this will allow the mixed modes to probe the very center of the stars. As we can see, that integral is highlighted in red on that propagation diagram. But also, the frequency of the mixed modes depend on the coupling between the P and the G cavity, and that coupling is directly related to the characteristics of the evanescent zone that is here represented in red. So mixed mode allow apparently to probe that very center of the star, but what about young subgiants? So in this study, because I wanted to constrain the Mainsequent structure, we focused on young subgiants in order to be as close as possible to the end of the Mainsequence. However, young subgiants exhibit a few number of G-dominated modes, let's say 1, 2, or 3. And so at the very beginning of my work with Sebastien, we wondered how to maximize the constraints on the structure, what is somehow the optimal number of visible G-dominated modes in order to get the best constraints and to be close to the end of the Mainsequence. Then we observed that if we have two G-dominated modes, and if we calculate the difference between those two consecutive G modes, we obtain, following the asymptotic theory formula, this sum of integral. I represented this sum of integral in that propagation diagram in gray, and we can see that that gray part is directly related to the part of Brunnweiss-Sala that is dominated by nabla mu, and that we actually want to probe. Therefore, this sum of integral directly gives interesting information for us. Which shows the interest to have at least two G-dominated modes to get this information. So I want to point out that I know that this is a crude approximation because the radial number of those G modes is very low, so we are not at all in the asymptotic regime. However, it may give us a hint of the mixed mode behavior. Also, as I said, the frequency of the mixed modes is sensitive to the coupling between the P and the G cavity, and therefore having several G-dominated modes allow to probe that coupling several times in different regions of the star and increase the constraints on the internal structure. So from that little study, we went to the conclusion that we wanted a target that exhibits two G-dominated modes in order to have the best constraint on the structure and to not be too evolved. So it's kind of a trade-off. Also, that star, of course, must be massive enough, because if it didn't have a convective core during its Mainsequence, it's not very interesting to study it, for us at least. And also, we had criteria based on data quality. So compared to more evolved stars, the frequencies of the subgiants are higher. Therefore, we need short cadence data from the Kepler data set if we want to retrieve the data from subgiants. And also, the star must be observed as long as possible in order to get the best spectral resolution. So all that finally led us to the choice of that kick star that is often nicknamed Mulder in the literature. So with the full Kepler dataset, it has been observed during 2.7 years. And so we extracted the frequencies from that full dataset. We can see on the figure 16 the observational echelle diagram of that star. Here we can see especially the dipolar ridge here on the right, and we can clearly see that typical pattern that is due to the two G dominated mode. It's not easy to say, that are here highlighted in red, and therefore the stars met our criteria. Also, it's a star that has been studied several times in the literature, especially recently, and using the seismic scaling relations, we saw that apparently that mass should be high enough for that star to have had a main sequence during its convective core. To have a convective core during its main sequence. So now that we have a star, but we must model it. However, the subgiant modeling, the seismic subgiant modeling, is notoriously difficult for two main reasons. So the first is that the frequency of the G modes is directly related to the central density of the star that evolves very fast because of the core contraction. And therefore, the mixed mode frequencies evolve very fast. I illustrate this on the figure 17 with a normalized echelle diagram. And we can see that the dipolar modes are very different, despite the fact that those two models are separated by only 10 million years. And this difference is more than 10 times the typical uncertainties of Kepler. So we need more precision than that. Also, as I said before, those G modes have a low radian number, and therefore we are not in the asymptotic regime. So we cannot use the same approach as we can use, for example, on more evolved stars. So because of that, the traditional methods encounter limits when it comes to study subgiants. For example, with grids, we require very fast steps, especially in age and mass. And therefore, we observed, especially in the framework of the Plateau space mission preparation, that interpolation both along tracks and across tracks is required if you want to get good models of subgiants using a grid. By the way, also, on-the-fly optimization, which I mean iterative methods, is not totally adapted because of the highly non-linear behavior of the mixed modes. So in my work, to model that star, I used an adapted method that is a forward method. So I used the MESA stellar evolution code with the step overshooting, and I computed the stellar oscillation frequencies using ADPLS with a surface effect that is reacted using the cubic term of the Bol-Gison prescription. So this method has been first developed by Sabatier in 2011 and improved for that paper. And the main idea of that method is to deal separately with the sensitive parameters, the mass and the age, and to deal with them separately from the others parameter, typically metallicity, mixing length, etc. So from that, we went to what I call the nested optimization, because it's composed of two steps. So the first step being within the second step. And that first step is what I call the mass age optimization. So its goal is to give a precise estimate of the mass and age of the star to reproduce the observed frequencies when the rest of the physics is fixed. To do so, we only reproduce two seismic observables that are the frequency of a G-dominated mode that I called here new G-dom, and the large separation called as usual delta nu. So to understand that, I represent here on that HR diagram two isolines. So the blue isolines is the region of all the models that have the same large separations, and the orange is all the models that have the same frequency of a G-dominated mode. And we can see that the two isolines cross in a unique point. This point can be reached by a unique evolution track, therefore a unique mass. And on that evolution tracks, we stop at one moment, therefore a unique age. So we conclude that reproducing only nu GDOM and delta nu allows to retrieve, when all the rest is fixed, of course, a unique couple of the mass F and the H. Just as an additional illustration, I represent here an Escher diagram of a model that is the result of that first step. We can see that the radial. So,
Hello, il n'y a plus de son.
There's no sound. Est-ce que vous m'entendez, Sébastien?
Oui, on t'entend.
Yes.
Oui, oui.
Ah, okay, okay.
Fine.
Okay, okay. So in that Escher diagram, we can see in gray the observations and in shallow symbols the model, and we can see that the radial frequencies are well reproduced as expected from the fact that we reproduce the large separation. And also we can see here that dipolar mode, G-dominated dipolar mode, the 11, the n equal 11, is also reproduced as expected from what I said just before. However, all the other dipolar frequencies are quite badly reproduced, which means that this model doesn't have, if I can say, the right internal structure to reproduce the observations. And we can play on other parameters in order to improve that fit. And this is the second step of that method, where this time we don't work on directly on stellar models, but on models that are already been mass age optimized and therefore reproduce delta nu and nu GDOM. The three parameters that we took for that study are the metallicity, the mixing length, the initial helium composition, and of course, the alpha overshoots. And thanks to that method, we obtained very good fits, the best model having a reduced chi-square of 3.2. And here I plot the Escher diagram of that best model. We can see that as expected, the radial modes as well as this frequency is well produced. But we can also observe that contrary to the former Escher diagram, all the dipolar frequencies are well reproduced, which apparently shows that the structure of that model is compatible with the observation. Also, I want to point out that the luminosity and the effective temperature are within one sigma of the surface observations. So the luminosity has been retrieved using a spectral energy distribution and the TF from spectroscopy. And so this is a quite good result, I mean, quite satisfying result, if I can say. But what about the constraints on the alpha V parameter? Because this was the main goal of that study. Well, thanks to that method, we managed to obtain a significant better fit when adding overshoots with the best model with alpha V equals 0.15. So here I represent the chi-square of the best model for every value of alpha V, and you can see that indeed the chi-square is lower for the 0.15 model, which means that it fits better the observations. Also, we can see that there is a strong worsening of the fit quality when we add more overshoot. The chi-square explodes when for the 0.25 value. I will come back to that a little bit later. And also on that plot with the color beyond the lines, I represented the contributions of different frequencies to the chi-square depending on their radial degree, on the degree, sorry. We can see in dark blue that the surface observations, it's almost invisible for most of the model, which means that they are well reproduced, as I said before. Here are the radial frequencies, here the dipolar frequencies, and here the quadrupolar frequency. And we can see that it's quite striking that what modes allow us to make the difference between all those models are indeed here the dipolar frequencies, and we can see that the fit of those dipolar frequencies is much better when we add overshoot than when we don't. This, of course, was kind of expected because the mixed modes are among those dipolar frequencies, but it's cool to see that we observe that as expected. So once that I obtain a constraint on that alpha V, I wanted to study a little bit more the relation between the frequencies of the model and the internal structure. Therefore, I used a large grid of mass age optimized model, so a grid that explores somehow a large space of parameters of models that I remind you, reproduced nu GDOM and delta nu. And especially, I studied the link between the frequencies of this model and two internal structure features that are highly related to the mixed mode frequencies, and that are the central density and the Brun-Weissala profile. So for the central density, quite strikingly, we observe that the scatter of the central density among all those models that are massage optimized is very small, less than 1%, which shows that reproducing the frequency of only one G-dominated mode already allows to have very strong constraints of that central density, which results in strong constraints on the stellar evolution. We can see that on that figure 22, where I plot the evolution of the central density with the age of different massage optimized models that have the same parameters, except different values of alpha OV. So we can see several things on that figure. We can see that, as I said, they all stop at the very same value of rho c. That is what I may call an optimal rho c for that star. But also, we can see that at some point in the evolution of that central density, we'll observe a very high jump in the central density. So this jump is related to the contraction of the core on a thermal time scale just after the end of the main sequence in order to ignite the hydrogen burning shell. And interestingly, we can see that these jumps get bigger and bigger as much as we had overshoot to the model. At some point, if we had too much overshoot, as it's the case with the 0.25, the brown curve, this optimal value of rho c will be reached during that thermal contraction time, and therefore the models that you obtain will not be compatible with the observations. Therefore, this could explain the strong worsening that we observed when we had, if I can say, too much overshoot, the high explosion of the K-square. So after that, I also investigated the Brun-Weissala profiles of all the models in that grid. And so here on that figure 23, I plot the Brun-Weissala profiles of all the models on that grid. So here as well, we can observe several things. So the first is that the very central part of that Brun-Weissala profile, below 0.05 solar radius, we can see that this part is well reproduced, similarly reproduced, by all the models of that grid, which means that reproducing one G-dominated mode through the massage optimization allowed to put very strong constraints on that part of the Brun-Weissala profiles. However, we can see that for higher radius, it's not the case at all, and there are several profiles among the grid for that part. So this is a little bit sad for us because, as I said before, that part is dominated by the composition gradients, and this is specifically the part that we want probe in order to have constraints on that star structure and the former main sequence structure. But the good news is that if we color those structure, those profile according to how well the model reproduces the second G-dominated mode, we can see that all the models that reproduce well that second G-dominated mode and that here are colored in dark are very well consistent one with each other, which shows that reproducing the second G-dominated mode allows us to have a stronger constraint on that composition gradients. So this is interesting because it's quite consistent actually with the small demonstration that I did at the end of the introduction about the link between the mixed mode frequencies and the composition, the part of the Brun-Weissala frequency that is dominated by the composition gradients. Another point of that study that actually took time a little bit more than expected is the study of microscopic diffusion. So in all the models that I showed you, microscopic diffusion is included. So I think that it's important for subgiant modeling for two main reasons. The first one is that during the main sequence, the heavy elements, because of the gravitational settling, will sink in the convective core and therefore will modify the evolution of the stars. But also for those stars, the chemical diffusion can have an impact on the composition gradient profile and especially smooth it as it's a chemical diffusion. However, we know that for that mass range around 1.2, 1.3 solar mass, it's a little bit difficult to include microscopic diffusion in the sense that it starts to be counterbalanced in the envelope by radiative accelerations that are that take a lot of time to compute. So it was not possible to include if all the models of that study. Therefore, I wanted to study the impact of the microscopic diffusion on the modeling of that subgiants. And so I redo the process without overshooting. And I observed that actually including diffusion allowed us to improve the quality of the fit. We can see that between the chi-square of the best model with diffusion and without diffusion, there's a difference of around 71. Also, we observed an improvement of the goodness of fit of the surface observables, as well as a change in the composition of profile. We can see that on the Brun-Weiss on the figure 24, where I represented the Brun-Weiss profiles of the two best models in blue with diffusion and orange without diffusion. And we can see that there's a strong peak in the model without diffusion that is smooth thanks to the chemical diffusion. We can also note that, except that, the two Brun-Weiss profiles are noticeably similar. Also, as I said, in the envelope, the gravitational settling starts to be counterbalanced by radiative accelerations, and therefore I try just to see to compute the best model with the adding of radiative accelerations. And actually, for subgiant stars, I didn't observe any significant difference. So something else also that we noticed when we model that subgiant stars is a very strong, degeneracy between the mass and the initial helium composition. So it's not a big surprise, because it has already been shown in Mainsequent stars as well as in subgiants by Tandali last year. However, it was quite striking for us because here I plot the H-shade diagrams, not of one, but of two models with quite different value of Y0. So the blue one that we barely see is Y0 equals 0.28, where the orange one that we see is 0.24. And we can see that the frequencies are very close, and despite the small Kepler uncertainties are barely distinguishable. And this can be an issue when we try to get the mass of the star because of that degeneracy. As we can see on that table, the mass of the two stars is quite different, around the 0.07 solar mass. And so if you want to retrieve reliable uncertainties on that mass, it's necessary to take into account that very strong degeneracy. So during that work, I also tried to model the star with diffusing overshooting, hoping to find any difference. However, once you find the FOV, so the diffusive overshooting parameter that is equivalent to the alpha OV, so the step overshooting parameter, actually, we don't find any significant difference in the quality of the fit. So we cannot distinguish between the two using this method. Also, in the observed spectrum, we detected a quadrupolar G-dominated splitted mode. And therefore, especially Sebastien managed to retrieve an approximate core rotation rate thanks to that mode, which is around 0.65 microhertz, and that is notably close to the surface rotation rate that has been retrieved by Campante et al. In 2011, and that is of half a microhertz, which will be compatible with the conclusion of Sebastien of his last year paper about rotation that is close to a solar body rotation for subgiants. So the current work is to use that method on other subgiants observed by Kepler, especially to see if you can obtain the trend of alpha OV, for example, with the mass as it been observed using Mainsequent stars modeling. So this is totally a work in progress. I will not talk more about this during this talk. However, here I plotted a chi-square versus alpha OV plot similarly to what I've done for the Mulder star. And we can see that we managed somehow to get a constraint for that star. So this is encouraging. So for the second part, it's not about this work about Mulder that has been published in a paper in Astronomy and Astrophysics 2 months ago, but it's about a work in progress that is not directly related to the seismic modeling of subgiants, but rather to some links that we found with Sebastien during the modeling of Mulder of the central mixing and the nuclear reactions and the impact that it could have on the convective core mass. So all that started when we tried to compare models that come from the Sesame stellar evolution code and the MESA evolution code. So here I plot the mass, the evolution of the mass with the edge during the main sequence of those two models. And we can see that there's a striking difference with a difference of mass of around 30% at 1 gig a year, despite the fact that those two models have the same parameters and the same prescription of overshoots. So we wondered why such a difference, what is the cause of that difference? So as I said at the first slide of the presentation, the car boundary is classically defined by the equality between the radiative gradients and the adiabatic gradients. Therefore, I represent here the radiative and adiabatic gradients for those two models. So we can see that the horizontal adiabatic gradients are totally equal between the two models. However, it's not the case for the radiative gradients. So here we can see that at the very center of the star, there's a quite strong difference between the two radiative gradients. And here the Sesame radiative gradients is around 1.5 times bigger than the MESA radiative gradients. So to understand a little bit, to continue to investigate why such a difference in the radiative gradients, I represent here the dependencies of the radiative gradients following the classical formula. And so the radiative gradients depend on the opacity of the stellar matter, on the luminosity, on the pressure, and on the temperature. When we computed those values using the model, we observed that the luminosity was the biggest contributor to that difference in the radiative gradients. So on what depends the luminosity? Who is the culprit? Well, we know that the luminosity depends mainly in models at the equilibrium on the nuclear energy production epsilon. And for this kind of star that we study, around 1.3 solar mass star, it's the proton-proton chain that dominates the energy nuclear production, and especially what is called the PP2 chain, and that involves those two reactions that involve the beryllium-7 and the lithium-7. And actually, if we plot the mass fraction of the lithium-7 for the two Sesame and MESA model, we can observe that there is an obvious difference between the two. So we can observe that here in the very core, in the convective core of the star, the lithium is homogeneous in Sesame, but actually it's not the case in MESA, despite the fact that we are in the convective core. The mass fraction of the lithium-7 is not. The lithium-7 is not homogeneous. So this is due actually to the way that the central mixing is implemented in the two stellar evolution codes. So it's instantaneous in Sesame, which means that all the elements are homogeneous in the convective core, but it's not the case in MESA. Actually, in MESA, the mixing is implemented using a diffusive approach, and therefore this explains why the lithium is not homogeneous in MESA. And as I showed here with that equation, the epsilon, so the energy nuclear production for that reaction in red, directly depends on the mass fractions of lithium, and therefore this explains the whole chain of reasoning. So the mass fraction will change the epsilon, that will change the luminosity, that will change the radiative gradients, and eventually will change the size of the convective core. So something else that maybe some people may wonder is what if we take both the lithium and the beryllium at the equilibrium? So it's an approximation that is often done in stellar evolution code. For example, in MESA, at least in the version that we use, the basic net reaction nuclear method, if I don't mistake, is the default nuclear reaction. And in that basic nuclear network, the mass fraction of lithium and barium are not took into account. And if we compute, if we do the same figure as the first one with two, this time MESA model, but using a different reaction networks, we can actually observe a difference in the convective core mass. Here we can see that the basic net model had a bigger convective core, at least more massive than the one that use the full net of nuclear reactions. So to understand this, it's a little bit more tricky, as we must remind that the mass fraction in the core depends on two physical processes that are the mixing and the nuclear reactions. So we know that the mixing in the core of the star is very efficient, and the typical turnover time scale for this kind of star at the core is around 4 days. However, for the nuclear reactions, especially for that pp2 chain, it's a little bit peculiar. So if we compute the equilibrium time scale of the lithium, we find 4 minutes, which is very small, which is less than the typical time scale of convection. Therefore, the lithium is, this is right at the equilibrium in the center of the star. However, if we compute the typical time scale of the beryllium, we found around 100 days, which is way bigger than the typical time scale. And therefore, the beryllium is not at the equilibrium in the center of the stars because of that efficient mixing. And the conclusion of all that is that actually, if you want to get a reliable core size in this kind of stars where pp2 dominates, we must take into account the time scale of the convection using a diffusive mixing at the center and the time scale of the lithium and the beryllium using a full nuclear reaction network. So this is totally in work in progress. This is not published. We, Sebastien especially, would like to see the impact of this on typical Mainsequent and why not subgiant seismic modeling. But I think that this could interest people among the audience, so I wanted to include this in the talk today. Also, I'd like to point out something that is a little bit tricky, is that actually we see an impact of the difference in radiative gradients on the convective core mass only if we include overshoot in the models. Therefore, if we want to reproduce such differences at home, you must take models that include overshooting. So I didn't include in that talk the explanation for that because it was a little bit lengthy and technical. So I thought that it was maybe out of the scope of this talk. So, in conclusion, in a paper that has been published in Astronomy and Astrophysics 2 months ago, I focused on the seismic modeling of a Kepler observed subgiant in order to retrieve constraints on its former convective core. So with the help of an adapted method, we obtain models that are in good agreement with the observation. And thanks to that, we managed to get constraints on the value of alpha of V. For example, we obtained the best model for alpha of V equals 0.15, and we observed the strong worsening of the fit for alpha of V superior to 0.2. Also, we noted the tight constraints, a tight link between the internal structure and the frequencies, especially a link between the central density and the frequency of 1G dominating mode, which eventually explain that strong worsening of the fit for alpha of V superior to 0.2, and that could be interesting, as subgiants could be an interesting way to put a maximum value on the alpha of V parameter, thanks to that strong evolutionary constraints. And also, we observed constraints on the compositional gradient profile, thanks specifically here to the second G-dominating mode that highly improved the quality, I mean, the consistency of the internal structure of the models. Also, we observed that including diffusion significantly improved the quality of the fit, as well as a strong Y0 mass degeneracy that was quite important for us to retrieve the most reliable uncertainties. And the current work using this method is to use it on other subgiants observed by Kepler in order to retrieve constraints on their on alpha of V parameter. Also, at the end of this talk, I talked about something a little bit peculiar, specific to this mass range where PP2 dominates. And we observed that if we want to have a reliable core size in model with overshoots, we must take into account the time scale of the convection and of the nuclear reaction, which means including a diffusive mixing in the center of the star and take into account the full nuclear reaction network. So that's all for my talk today. Thank you very much for your attention, and please ask a question if you have. Thank you very much.
Thank you very much, Anthony. Are there questions in the audience? Yes, Connie?
Hi, Anthony.
Hi.
Thank you very much, and congratulations on a very good talk. I very much enjoyed it. Just one tip, if you want to refer to the G modes, we have now done a much more extensive study in the PhD of Mai Petersen, and she will very, very soon put that in the literature. As it happens, the preference to a diffusive overshoot was for a star that we picked with exceptionally low mixing. So we now have a much bigger diversity, and your work is actually completely complementary to what we are doing. So I'm very excited to see the results of your additional subgiants. Of course, on the last part, we have CNO dominated core. So this is not something we can compare. But I was wondering how, if you at all, what we need in the more massive star is envelope mixing. It's crucial. And we actually find penetrative convection and shear mixing to lead to far better models now. We have done 26 stars. So I wonder if that is something you also plan to investigate. I understand you are close to finishing, but maybe you can take it up as in your postdoc, because we have investigated 8 different models of mixing types now. And so again, we are in a different mass regime than you, but I wonder how we can backtrack it to your stars, so or forward it to your less massive stars. Have you looked at that to change to penetrative convection and to include envelope mixing, or not yet?
So by envelope mixing, so you don't talk of the convective envelope here, but rather on the radiative envelope for more massive stars, I guess.
Part, yeah.
And so we didn't look at that specifically for subgiants. Also, about your other question, I think it's related with the difference between the penetrative convection and the overshoot, as they so-called in the Zahn paper, that differentiates in the radiative gradients, I mean, in the overshoot region. Is it that?
Yeah. Yeah.
We didn't try to investigate this. I am pretty sure it's possible with the MESA to tweak it and therefore to probe that. However, no, we didn't try. I'm not totally sure we could get constraint on this very, how to say, on this very precise thing using a subgiant modeling. However, of course, it could be interesting, but I'm not sure we could get such constraints using this indirect way to model main-sequent stars.
Yeah, you could talk to Matthias Michielsen, who is doing that for GMODs, or to Joey Momberg, who is in Toulouse now, so
okay.
It's close to you. Okay, thank you very much.
Thank you very much.
Okay.
Thank you, Connie. I had seen Saskia, but maybe the hand lowered. Saskia,
I did lower the hand, but I can still ask the question if that's okay.
Sure, yeah.
I was wondering, Anthony, thanks by the way for the very nice talk. So you had this chi-square differences between having diffusion included and non-diffusion included. And I was actually wondering if you took account of the fact that you have more free parameters if you include the diffusion, and so how significant that difference actually was.
So what supplementary free parameters are you talking about for the?
If you include diffusion or you don't include diffusion.
You mean it's a one supplementary free parameter?
I mean the difference was, there was a difference indeed, but I was just wondering how significant the result was.
So it was. I mean, the chi-square difference is high enough to be significant despite the difference in the free parameters. However, I don't remember, at least writing in the article, something directly related to taking into account one more free parameter when we included diffusion.
Okay. And I had a second thing, and maybe that's just me not understanding it, but I think if you go back 2 slides, yes, here. So you say the nuclear reaction. So if I understand it correctly, so the nuclear reaction of lithium take place on a 4-minute scale, while your convection is taking place on a 4-day scale. And so I didn't understand why that would be an equilibrium, because I mean, the reaction rate of lithium is much faster than the convection, if I understand it here. So I would then intuitively say that it's not an equilibrium, but maybe I've misunderstood something here.
I think here what I mean by lithium is that the equilibrium is become here the tau Li7 is actually the equilibrium of the time scale. So it's the typical it's the time scale of the equilibrium. So it's the time scale when the modification of Li7 because of those nuclear reactions is equal to 0. So when it reaches the equilibrium, which means that the mass fraction of the lithium is defined, if I can say, by the physics of the nuclear reactions, and the mixing is not efficient enough to have a significant impact on the mass fraction, which means that mass fraction is dominated by that nuclear reaction process and not the mixing in the core, as it's very fast. It's that second here red reaction is very easy to do, if I can say, and therefore the lithium will quickly reach the equilibrium way faster than the modification that could have been done because of the mixing. And it's not the case of the beryllium because the electron capture is way less efficient. So
okay, and I understand. So it's in chemical equilibrium there because it's so fast, and
yes,
I had understood that differently. Okay, thank you very much for the explanation.
Thank you.
Thank you. I have Jorn and then Yaguang. Jorn, please.
Thank you very much for a really excellent study and excellent talk. I should go back and check your paper. I've got a couple of comments and questions. First about which was addressed also by Connie. In your model with diffusion, I guess that the surface composition of the star during the main sequence phase would be completely off because you're going to lose all the heavy elements and all the helium from the envelope. And then once you get to subgiant branch, that you get deeper mixing and then you restore the composition in the envelope. So it's interesting, and you might take a closer look at that the change in structure during the main sequence phase has no impact on the model once it gets to the subgiant branch. I don't know whether you have any comments on that.
Well, actually, so that's right. That if we take only into account gravitational settling for this kind of star, we will have a depletion of heavy elements in the surface during the main sequence. For example, this is why supplementary mixing is often added. For example, turbulent diffusion. However, here I think so. You mean that the fact that we are not in the main sequence anymore, but in the subgiant phase, there's somehow of the reset of the structure, and therefore we don't observe such differences. And this is something that I don't know if I'm right, if I well understood the question, but is actually related to the fact that we didn't observe any difference when we added radiative accelerations. So in a paper by Morgan Dill, he observed that adding a radiative acceleration had an impact on the modeling, on the seismic modeling of Mainsequent stars for this mass range, but it's something that we didn't observe for subgiants. So, so maybe yes, this could explain the difference in the structure between the two phases of the star.
Well, I think the reason that you don't see it on the subgiant branch is that you get a deepening of the convection zone, so you mix up all the material that has settled during the main sequence phase, because that would only affect the outermost layers.
Absolutely, the convective envelope is growing during the main sequence.
Yeah, but it would be interesting to look at the time evolution of the heavy element abundance during the main sequence up to the subgiant point where you are now. The second point is also a bit related to, if you go back to the buoyancy frequency for your model without and with diffusion. It's interesting that they're so similar apart from the spike. And I guess the spike occurs because of the increase in the size of the convective core during part of the evolution that leaves behind a discontinuity in the composition. And one point I just want to make here is that computing frequencies for a model like that is non-trivial. And it might be worth taking a look at how ADIPULSE handles it in your case, because precisely that issue is something I've been working on recently in upgrading ADIPULSE. And I'm not sure that Jaya is doing so great either on that actually, before Connie starts talking about other pulsation codes. So maybe at some point we should take a look at that, the frequency calculation for the non-diffusion model and see whether we can, there's some problems there. Okay. But thanks again very much. It was really a pleasure.
Thank you. So about your last point is that if we have this kind of Brunn-Weissala structure with spikes and stuff like that, maybe it's interesting to have a look at the in that case ADPLS code to try to manage this kind of peculiar models. This is
yeah. Well, the code does its best, but I think it's been learning since the version you probably have.
Okay. Thank you very much.
Thank you, and we have Yagwang.
Yeah, thank you, Seb, and thank you, Anthony, for this wonderful talk. These subgiants are really, really amazing objects. So I have two questions in particular. And the first question is about your treatment of overshoot. So just like you found a degeneracy between the helium abundance and mass, I wonder whether there is any degeneracy between the mixing length parameter and the overshoot. That is the first question. And the second question is about the choice of surface effect. Do you think for subgiants, there is an advantage in using the cubic inverse term to describe the surface effect compared to other descriptions like the cubic term alone or other, for example, parallel descriptions? And do you think the descriptions for the surface effects behave differently for mixed modes and the radial modes? And thank you, that's my questions.
Thank you very much. So about the alpha overshoot versus alpha convection degeneracy, I'm sorry to say I must maybe go back to the article where I put the characteristics of the best model for every value of alpha OV, and I don't have the values in mind right now, so I cannot say if there's a specific trend for that. I don't remember specifically, but I cannot say for 100% sure that it's the case. So I think, yeah, I should, you can maybe go back to the article and see the figures there. For your second question about the surface effect. So this was, this was a question that we talked about with Sebastien a long time ago, and that we used so that only the cubic term, because the inverse term of that Boulogne-Guizon effect that is not very important for subgiants. However, we didn't do in that case systematic studies of the impact of that surface effect in the quality of the fit of those subgiants. However, we believe that that it shouldn't have a big impact, because here the G-dominated modes have a high inertia and therefore are less impacted by the surface effect. And also, we didn't observe any trend on the P-dominated dipolar modes that could lead to a wrong misuse of the surface effect correction. So I don't know if I answer entirely your questions. Maybe it's something that we could investigate more in depth. But I think this is all the information that I can give you right now. Thank you very much.
Yeah. Thank you. No worries. There are lots of questions to answer.
Okay, thank you. I have now Matthias Mikkelsen and then Thierry Apourchot. Matthias?
So hi, thanks for a very interesting talk. If I understood your modeling methodology correctly, you first fix the mass and the age of your star, and then afterwards you go and take a look at the other parameters, right?
Yes, so this is a very tricky part to understand.
Yeah, but it's just I was wondering, because afterwards you vary the alpha parameter, so you overshoot. But wouldn't you expect a degeneracy between the initial mass of your model and the overshoots, so the alpha parameter? Because yeah, well, both influence the size of your convective core effectively. And especially if you're also looking at modes with the G mode properties, they are very sensitive to the size of your convective cores. So would that influence your results if you vary both of them simultaneously instead of fixing one and then looking at the other?
So here what I do is actually it's a bit another way around, which means that using traditional techniques, I will fix those three parameters: metallicity, mixing length, Y0, and alpha OV, and then with those parameters fixed, I will try to reproduce those two seismic observables, and therefore to have the mass and the age that manage to reproduce as best as possible the observed frequencies with those parameters that are fixed. So it's a thing that is a little bit tricky. This is what it's called a nested optimization. So I think this maybe could answer your first question. Also here, so apparently here we didn't observe a total degeneracy between the mass and the alpha OV, because we managed to differentiate models depending on the alpha OV, despite the fact that the mass for all those models was the free parameter, and that we modified the mass in all the models in order to retrieve to get the best model, to reproduce the observed frequencies. And therefore, we took into account this. We don't have a fixed mass and therefore modify the alpha OV. Of course, this I think would not be an approach that would be good. So does it answer your question?
More or less. Yeah. Thanks.
Okay. Don't hesitate. I mean, if I did not answer well, don't hesitate to send me an email.
Yeah, it's just that. Well, I'm not. Well, personally very familiar with fixing a parameter and like the nested approximation that you did, let's say.
Yes,
sorry,
yes,
the nested optimization.
Yeah, but it's totally normal that you are not familiar, because it's actually something that we only us use. So yes, it's a bit difficult to introduce. But,
okay, thanks.
Thank you very much.
Okay, thank you. Thierry now, Thierry Apourchot.
Yeah. Thanks, Anthony, for a very stimulating talk, especially for pointing out that the modelers, they don't know what they're doing, as usual. And the other, the question I had was related to the surface effect. In my opinion, it's true that the the G-dominated modes are not sensitive to the surface effect. So my question was, I guess the chi-square you have for the frequencies, I'm not sure it is 3.2, but maybe you can confirm that online. Is it?
The reduced chi-square, yes, it's 3.2 for the best model.
Okay, all right. It's reduced to the number with respect to the number of frequencies, or of
frequencies of observables. So here we take into account also surface observables minus free parameters.
So my question is a bit deeper. That have you considered trying to not to do surface correction, but using the ratios especially because the G mode dominated can be used to anchor your model. So instead of doing surface effect, have you tried considering doing the ratios instead?
But so I believe so ratios for subgiants. So I'm not entirely familiar. I mean, I know the process of using the ratios. I'm not entirely familiar with. I know it's a method that is used for Mainsequent stars using some patterns that we can find among the P modes. However, here I don't know if we can find such patterns, and especially because of the presence of G-dominated modes. This pattern that is directly related to the pressure-dominated modes could be a little bit, I would say, modified by this.
Right. What you would do would be to exclude those G-dominated mode for the computing the ratios. But my question was related to the fact that the frequencies are so close, even with the surface correction. So maybe it's just what I'm talking about is just useless.
I don't know. I mean, here for the ratio, also for the dipolar modes, even if we get rid of the J-dominated modes, actually all the dipolar modes are mixed modes, and therefore they have energy in the G cavity, and there are no pure pressure modes except maybe some here, that mode here for that Escher diagram. Therefore, I'm not totally sure it will be easy to totally get rid of the influence of the G modes on the frequencies of the dipolar frequencies of that model. And also here for that whole processing, so for that whole modeling process, we did not observe differences among models that could be mainly due to surface effects. So we didn't think with Sebastian that it could be a big problem in this case of star.
Okay, that's fine. That's what I wanted to hear. Thanks.
Okay, I'm told by the organizers that we need to wrap up. So maybe one last question by Victor, a quick one, and then we'll stop.
Thanks, Anthony. This was a very, very nice talk. I also don't understand your optimization process, but I won't ask about that. Maybe I'll just try to read the paper better. I was just wondering if it was very interesting that you showed that what you found about the central density. And I was wondering if you thought about trying to use this to constrain the size of the helium core size. Is that something you have looked into?
The helium core size. So actually, what we can see here is that that peak is due to the hydrogen burning shell, and we can see that that position of the hydrogen burning shell in solar radius is actually quite well constrained by reproducing the G-dominated modes. And I think that of course I think that the position of that hydrogen burning shell is directly related to the size of that helium core, and probably this is the way, and probably using this method we have actually a very strong constraints on the size of the helium core. However, it's not something that we directly explicitly said in the paper. We did not focus particularly on that helium core, inert helium core, but rather on the hydrogen burning shell. But I think that both are related.
I mean, I think there's a relation there also because you use a value of overshoot, so you're basically measuring the integrated overshoot throughout the main sequence. But you could probably reach the same size of the helium core with a ramp overshoot, for instance, going from a small value to a larger value throughout the main sequence. And maybe you could disentangle those two effects with this technique. That would be something very, very interesting, I think, to look into. But thank you again for a very, very excellent talk.
Okay, thank you very much.
Okay, thanks a lot. So if you have other questions for Anthony, I guess you can send him an email about this. And with this, I will give the floor back to Rita. Thank you.
Thank you.
Yeah, thanks a lot, Anthony, for a very interesting talk. And I think you will receive a couple of questions by emails. Thanks a lot, Sebastian. for handling this talk and questions. Thanks everyone. So we see you in 2 weeks for a talk by Diego Godoy Rivera from Ohio State University, and he will talk about gyrochronology. Thanks a lot. See you then.
Thank you very much. See you.
And the people from the steering committee can stay around for 5 more minutes, please.
Bye.
Bye. Thank you.
Bye, everyone.